So what we've been doing over the last few lessons is finding the equations of different lines, how we find key points, points of intersection of tangents, normals, and then yesterday we looked at the chord of contact. So the question is, what do we do with all that information now that we can find them? And we're going to look at a couple of different geometrical theorems, but basically, yes, we use them to prove different things about the parabola. So here's the first one, focal chords. Mentioned a bit about focal chords right back when we looked at how to find the equation of the chord. Remember, focal chord is a chord that goes through the focus. We're going to prove that when we draw a tangent from the endpoints of the focal chord, they will intersect at 90 degrees, but also they will intersect on the directrix. So that's the first one we want to prove. Now you may remember back when we looked at chords, I went and proved PQ equals -1. That was the condition for it to be a focal chord. So the first part of this question would be to go and prove PQ equals -1. So if you see a focal chord question and they ask you to prove something, there's a strong chance you're going to have to use this relationship. So you go and prove PQ is -1. Now remember, we found that the slope of the tangent was always equal to the parameter. So that would be the next thing we'd go and do. So I know the slope of the tangent at P is little p, and at Q is little q. Combine these two things together, and what are we saying? We're saying that the two slopes multiply together to give -1, which is the condition for what? Perpendicular lines. So hence, we've proved the first part, intersect at right angles. So, all right, yep, PQ equals -1. So therefore we know the tangents are perpendicular to each other. The second part we want to prove is that they meet on the directrix. So we're going to have to find the point of intersection, of our tangent. So mind you, we really only need the y value. Remember, the equation of the directrix is y equals -a. So if we can show that the y value is -a, then it must meet on the directrix. Well, when we did go and find that point of intersection, the y value was APQ. APQ, but again, PQ is -1. So I can substitute in and I get y equals -a. So yep, meets on the directrix. So that proves that particular geometrical property. If you always have a focal chord, the two tangents will always meet on the directrix and they'll always meet at right angles. This is probably one of the more, I don't know if famous is the right word, but the more interesting properties, and it's very relevant, the reflection property. Now I don't know whether you realise this or not, but things like car headlights, they are actually parabolic reflectors. Okay? I mean, when you look at them, sometimes they look like rectangles on some cars, sometimes they look like circles. But if you were to actually cut it open, the shape of the reflector is a parabola. And it's for this very important property. Now, the words might just seem like a lot of jumble, but technically there is. Any line parallel to the axis of the parabola is reflected towards the focus, and any line from the focus of the parabola is reflected parallel to the axis. Thus, a line and its reflection are equally inclined to the normal as well as to the tangent. What on earth does that all mean? Okay. So what it's saying is, well, this is the one where it's collecting light, but imagine this is the other way around. If you place a light bulb, say that is a parabolic reflector, you place a bulb at the focus, then all the light rays will go off, but they will always bounce parallel to the axis. So in other words, they'll go straight. Every single beam of light, bang, gets reflected straight. Now, you've got a headlight of a car, that's quite useful. Because when you're driving, you're not really interested in what's happening on the right, what's happening on the left. You want to see what's on the road in front of you. So it collects all that light and pushes it in front of it. So what I always find amazing is this is a property that they discovered thousands of years ago when they were playing with geometry, and obviously headlights and things like that have only been around for a couple of 100 years, and they've been able to use that property to do something really useful. So we're going to prove this particular property. So here's my standard parabola. Focus is at naught A. The light ray is going to come out, hit the parabolic reflector at P, and we want to prove basically that that light ray will go parallel. So I want to prove that angle SPK SPK is equal to CPB. Or in other words, to put it in very simple terms, which you've probably heard of when you're in science, the angle of incidence is equal to the angle of reflection. That's basically what we want to prove. Okay. Well, if CP is parallel to the y-axis, fingers crossed that's what we want, then hopefully we can prove that these angles will end up being the same. So we're going to assume CP is parallel to the y-axis. So the first thing I'm going to do is find the equation of that tangent. And you might remember that the general equation was y equals px minus ap squared. Then I'm going to find the y-intercept. Now that of course happens when x equals 0. And so it'll be 0 negative ap squared. Okay, so my distance from the focus down to the intercept, well that was ap squared, plus up to the focus is a, so the total distance is a plus ap squared. We want to find distance ps. This is the long way of finding distance ps, by the way. Go and use the distance formula using the two coordinates. But it turns out to be a p squared plus 1. Whenever you're finding a distance to the focus, now usually that distance is going to be at an angle, so yes, you go and use the distance formula. But if you take advantage of the definition of a parabola, then you can always find a vertical distance, because remember, the distance to the focus is equal to the distance to the directrix. So to find the distance from P down to the directrix is a lot easier, because it's just a vertical distance. The directrix, remember, y equals negative a, so we'd have a units going up to the x-axis, and then we have another ap squared going up to the point, and so the distance is just ap squared plus a. Lot quicker than using the distance formula. So keep that in mind when you're doing some of these problems. If you have to find a distance to the focus, take advantage of the definition of the parabola. Instead of finding that distance at an angle and having to use the distance formula, find the vertical distance to the directrix, because they will be equal. That's the definition of the parabola. So right, however we do it, we end up that, hang on, these two distances are equal. Well, that means that triangle is isosceles. Now, if that's true, we know the base angles in the isosceles triangle are equal. So I know SPK is the same as SKP. But then have a look at their parallel lines. Remember, we assumed CP was parallel to the axis of the parabola. So SKP is equal to CPB, corresponding angles. Well, therefore, SPK is equal to CPB. That's what we were trying to prove. So the angle of incidence does equal the angle of reflection. That's just one way of proving the reflection property. There's lots of different ways, and in the actual exercise they'll probably get you to go through some different ones.